Check it out now, y'all.
NanoHub U, online instruction.
This week we're going to start our discussion of special relativity. So we're going to put aside our interest in quantum mechanics. We're going to try to describe in a simple way some of the essential features of space and time that were discovered in the early 1900s as a consequence of some very interesting experiments that were performed at the time. Now this first lecture is going to be an introductory lecture, and in particular we're going to discuss inertial reference frames and Galilean transforms. And I think it's important for you to understand these concepts reasonably well before we launch into our discussion of Einstein's theory of special relativity. Very often I'm asked the question, why do engineers need to study special relativity? It's kind of an esoteric subject, and it applies to objects that are moving close to the speed of light. My answer to that is that this is a very interesting subject, and it has a lot of interesting twists and turns. And for you to understand the context of science in our modern time, it's really important for you to understand how time and space are coupled as described by special relativity. The other point I'll make is that I've learned that if you learn something new, your head will not explode. So there's no reason for you not to study this subject. It's just inherently interesting. And as a consequence, you'll learn some new facts that might be relevant for your understanding of other effects and phenomena as you move through your life as an engineer. So this first lecture is going to be a little bit longer than our normal 25 minutes. I do this on purpose because I really want to discuss in a general way some of these concepts that are mentioned or briefly mentioned in many textbooks, but they're really not discussed or illustrated in a convincing way. And I personally believe that if you want to understand the context of special relativity, you have to first understand the mindset that people had before special relativity was invented. So that's the pretext of this first lecture, which is an introductory lecture. The concept of relativity is usually associated with Einstein, but really, if you think about it, it's related to a very long effort to understand our place in the universe. And this effort goes back 2,000 or 3,000 years. You'll recall that initially the Earth was thought to be the center of a flat universe, and the Earth was at rest inside this universe, and everything revolved around the Earth. That point of view fell into disfavor in the 1500s because new experimental data showed that the Earth was actually moving or orbiting around the Sun. That was a very hard fact for many philosophers and politicians at the time to accept, but experiment was telling that the Earth is not at rest, and so there has to be a different viewpoint of what the universe is. And that view of the 1500s should be contrasted to the view that developed in the early 1900s, when it was basically realized there is no center to the universe. There's no place in the universe that is at rest. The universe is not flat, so that everything relative to a central point is, or framing a discussion about motion relative to a central point is counterproductive in many ways. So what is relativity? With that brief background, what is relativity? Well, relativity is an idea, right? And the idea is that the laws of the universe are the same no matter what direction you are facing, no matter where you are standing, no matter how fast you are moving, so long as the speed you are moving at is constant with time. right? So this is a very general statement. It has very broad implications. And in the next 2 weeks, we're going to try to explore some of these concepts in a mathematical way. So, in my opinion, the scientific origin of this concept of relativity really goes back to the early 1600s when the scientific problem of the century was, does the Earth move? Right? So you can contrast that to your favorite problem of the century we're currently in. There are many problems we're facing. Depending on what newspapers or news broadcast you listen to, you'll find some reoccurring themes about scientific problems that confront our world today. But in the early 1600s, the big issue was, is there any way we can prove beyond a shadow of a doubt that the Earth moves through space? So there were arguments pro and con. The arguments against the Earth's motion was that there's no speed sensation when we stand on the surface of the Earth. That seems to be very clear to us even today. But people like Galileo had counter-arguments to that. And he said, well, just do a simple thought experiment. He says, suppose you're in the bottom of a ship and the ship is moving with a constant velocity. Is there any experiment that you can do to distinguish between the ship moving at a constant velocity or the ship standing still at a dock? So the experiments you have to do have to be below deck. You can't look out the window of the ship. And Galileo thought about the problem, and he concluded that you can do any experiment you want as long as the ship is moving at a constant velocity. You won't be able to tell the difference between a stationary ship and a ship that's moving. So, you know, the type of experiments that you could do in the 1600s were pretty simple. I'm trying to come up with an analogy, maybe that's a bit more of a modern equivalent. And the idea I'd like you to think about is trying to play pool on an ocean liner that's moving across the ocean. So if this pool table is submerged in the decks of the ship, and if the ship is moving at constant velocity, what I'm telling you is you can play a game of pool without any problem, right? The motion of the cue balls, the motion of the balls, the way the balls drop into the pockets, everything will be the same as if the ship were standing still. If the ship starts to change its velocity, though, during the time that ship is changing its velocity, then you're going to have all kinds of weird effects occurring on the pool table. The balls will actually start to jiggle around and move just because they're going to experience an acceleration due to the change in the velocity of the ship. So Galileo's conclusion about this ship analogy is that as long as the ship is moving at a constant velocity, you can't determine. You cannot do an experiment on board the ship to tell what the velocity of the ship is, right? So the velocity could be the ship could be moving at a velocity of v or 5v or 10v, right? And as long as it's constant, no experiment you can do to tell whether it's constant or at rest. So this simple line of thought gives rise to the concept of an inertial reference frame. And Galileo's thought experiment is embodied in this inertial reference frame. And the notion is that the laws of physics are the same in all inertial frames, and that no inertial frame is different in any other from any other in any important way. So this concept of an inertial frame of reference is used repeatedly in our discussion of special relativity. And so it's very important for you to understand what the background is and what the concept of this inertial frame of reference is all about. So what's an example of an inertial reference frame? Well, you could have many possible reference frames. One example is the one that we've created on Earth, where we define directions in terms of north, south, east, and west. and where we define angles in terms of the zenith and the horizon. So, you can define angles of stars or planes that are flying with respect to an angle that's measured from the horizon. This is just one example of a possible inertial reference frame. A more scientific definition of an inertial reference frame is that is by making a statement that all the laws of physics take their simplest form in these inertial frames of reference. So how do you know whether a particular reference frame is inertial or non-inertial? Well, what you do is you do some experiments, and if, for instance, Newton's laws of motion explain the experimental observations that you make, then you're pretty confident that you're in an inertial reference frame, right? So what are Newton's laws of motion? Well, there's 3 of them, but in particular, if you take a free particle and that free particle travels in a straight line at a constant speed, or if it's at rest, then that satisfies Newton's first law, which is often referred to as the principle of inertia, and so that would therefore represent an inertial reference frame. There's an interesting question. If you pick one inertial reference frame and you do all your experiments in that, and a friend of yours picks a different reference frame, inertial reference frame, and does his experiments in that second reference frame, how are the 2 reference frames related to one another? That becomes an important problem because you'd like to be able to translate the experiments done in each inertial reference frame and relate them back to experiments, identical experiments that were performed, let's say, in a second frame. Well, these 2 inertial reference frames are related by something called a Galilean transform, and that Galilean transform is going to be the subject of the remainder of this lecture. What I will say up front is Einstein was able to show that this Galilean transform between 2 inertial reference frames was incorrect. In principle, that the Galilean transform only applies for small velocities, and when velocities start to become comparable to the speed of light, then you have to use a different type of transformation. A different type of transformation is referred to as the Lorentz transformation, and that will become a subject that we'll discuss later on in this week. That's the mathematical basis of special relativity. So, what happens if you choose a non-inertial reference frame to do an experiment? Well, the simple answer is that you're going to find that you're going to have to invent all kind of fictitious forces. And these fictitious forces are going to depend on the motion of the observer, and therefore these fictitious forces are going to vary with the motion of the observer, right? So if these fictitious forces vanish, then you know you're in an inertial frame of reference. But if you do an experiment, you have to invent all kinds of additional forces to describe, let's say, the motion of a particle, right? Then you're pretty sure that that frame of reference that you've chosen is non-inertial. So can you give an example, or can I give an example of a non-inertial reference frame? And the answer is yeah. I can imagine a reference frame that's rotating quickly about a point on the Earth's surface. So this would be referred to as let's say a merry-go-round that you commonly see in playgrounds. If you get on that merry-go-round and you start it spinning very rapidly, while you're standing on that merry-go-round, you're subjected to a centripetal force due to the rotational motion, and that centripetal force it's due to the fact that the merry-go-round is constantly has a constant angular velocity. There's an additional acceleration that pushes objects, that attracts objects in toward the center of the motion, and that additional acceleration renders that reference frame non-inertial. And so what we like to do in the next couple of slides is try to demonstrate that to you in the form of a simple computer simulation, just to fix the ideas so that they're clear in your head. And so what we've done is we've gone to this website, which I list here. You're all welcome to go there and run this simulation on your own computer. But basically what we've got is we've got two situations. We've got one of these rotating platforms. The platform is rotating at a constant angular velocity omega, right? And there are two scientists, scientist 1 and scientist 2, right? Scientist 1 is going to have a ball, and he's going to, at a particular point in time, he's going to roll the ball so that scientist 2 can catch it. And we're going to view this simple experiment from two different reference frames. One reference frame is going to be positioning a camera attached to this rotating platform, right? And so the camera is going to see this, scientist number 1 is fixed. So scientist number 1 will be stationary, right? And scientist number 2 in this reference frame attached to the rotating platform, scientist number 2 is going to appear to rotate around a stationary platform. That turns out to be a non-inertial reference frame because the platform is rotating and we're using it as a reference frame. The other possibility is to attach a camera to the Earth, which scientist number 2 is sitting on, right? Scientist number 2 will then appear to be stationary in this reference frame, right? And this reference frame attached to Earth is a very good approximation to an inertial reference frame. And what we're going to just do is we're going to ask the question, what is the apparent motion of this ball when scientist number 1 throws it to scientist number 2 in each of these two reference frames. So scientist 1 is not going to throw the ball to scientist number 2. He's actually going to roll it along this rotating platform. And we're going to assume that there's no friction between the ball and the platform as the ball rolls. And we're just going to ask the question, what does the motion look like when viewed from these two reference frames? So hopefully the premise of the experiment is reasonably clear. This is an attempt, the simulation is an attempt to show you what a non-inertial reference frame looks like. So the next slide here, I've actually put an animation of this experiment, and we'll just run it real quick so you can see what it looks like. Here's our two scientists. We're going to start the platform rotating, right? This platform here has a camera that's attached to it. This platform here has a camera that's attached to the Earth, right? So this scientist is going to appear stationary in our non-inertial reference frame. This guy here is going to appear stationary in our inertial reference frame. So let me just run the video right up to the point where scientist 1 is ready to release the ball. Okay. So what's the relative motion going to look like in the two reference frames? Well, in this video, what we've done is we've slowed the speed down so you can actually follow what's going on. And then in addition, I've added trajectories, right? I've added trajectories that help you visualize where the ball is gonna move. So let's run this. So now we're just stepping through the motion, right? You can see what's happening. In our non-inertial reference frame, this guy is fixed. In our inertial reference frame, this guy is fixed, right? They're going to do the same experiment. When this guy here gets up to the top, this guy is going to release the ball, right? The ball is going to follow a curved path in the non-inertial reference frame. In the inertial reference frame, the ball travels in a straight line. So at the end of the experiment, right, the result is the same. This guy, right, this scientist number 2 has caught the ball, right, and he's at this orientation with respect to scientist number 1. The thing that's different is in the non-inertial reference frame, the ball followed this very screwy-looking path. Here, in the inertial reference frame, the path of the ball was straight. So, how do you describe the difference between these two experiments? Well, anytime the ball moves anytime the ball deviates from a straight line motion, right, that implies there's a force acting on it. So there clearly has to be some additional forces acting on the ball because you're viewing the experiment from the non-inertial reference frame. When you view the experiment from the inertial reference frame, the ball moves in a straight line, which is what you would expect from Newton's laws of motion. So the next slide just tries to make that case. This is an example. If you're trying to describe the motion in the inertial reference frame, Newton's second law, F equals ma, applies. If you're trying to describe the motion of that ball in the non-inertial reference frame, you have to invent a new force called F prime, right? When you invent that new force F prime, then you can rewrite Newton's laws in this simple form, but F prime is going to be the original F plus terms that take into account the angular velocity of the reference frame as it's moving, right? So these are the Coriolis force, the centrifugal force, and the Euler force. And in this case that we're dealing with, the Euler force is 0 because the angular velocity is assumed constant with respect to time. So, much more complicated equation of motion in a non-inertial reference frame than in the inertial reference frame. That's the bottom line. That's what you have to take away from this discussion. Technically, the Earth is strictly not an inertial reference frame. And the reason it isn't is because the Earth rotates around the Sun. In addition, the Earth is spinning about its axis. And then the third issue is that if you drop something on the Earth, it's going to accelerate downward due to gravity. So all three of these effects have to be taken into account if you're going to properly describe an experiment that's performed on the surface of the Earth. Fortunately, if the time scale for an experiment on the surface of the Earth is small compared to, let's say, the rotational motion of the Earth, then you can just approximate the forces acting on the object due to gravity alone, right? And then you can revert back to Newton's laws of motion. So the key point is these non-inertial reference frames, which includes the Earth, technically the Earth is non-inertial reference frame, they can very closely approximate an inertial reference frame as long as you do an experiment quickly enough that the motion of these objects don't come are not important. So for instance, in the example where we had the rotating platform, right, the time it took for the ball to go from scientist 1 to scientist 2, that time was comparable to the rotational speed of the rotating platform. And so therefore it became important to take into account the non-inertial reference frame associated with a reference frame attached to the platform itself. Okay, so it's a long story, but it tries to give you some feeling or some intuition about these inertial versus non-inertial reference frames, and this becomes an important consideration when we delve into special relativity. So if we have an inertial reference frame, and from now until the end of our discussion of special relativity, we're always going to assume that our reference frame is inertial, right? I want to make the point that if you have two inertial reference frames, simple measurements are different. You get different answers, right? And so this may be surprising to you, but it's not really. It's pretty much common sense. So I want you to think about two inertial reference frames. One is at rest, so this reference frame here has a ruler associated with it, and it measures the position of, let's say, a baseball. And the baseball in this blue inertial reference frame is at +2 meters. Another reference frame that's indicated by the red reference frame. The red reference frame has a red ruler associated with it. And anybody in this reference frame is moving by the blue stationary frame at, let's say, a constant velocity, in this example, of 1 meter per second. Okay? So at the particular instant in time when the two origins of these two rulers happen to line up, we can use that happy event to define t equal to 0. And when that alignment occurs, the guy in the red reference frame will measure the position of the ball to be at plus 2 meters, and it will exactly agree with the measurement of position of the baseball by the guy in the blue reference frame, right? But if you just wait a few seconds longer, right, you wait 2 seconds, the red reference frame keeps moving at 1 meter per second, and you now ask the two guys to make a measurement, right? The guy in the stationary reference frame is going to say the baseball's still at plus 2 meters, but the guy in the red reference frame that's moving at a velocity of 1 meter per second, he's going to say, oh no, wait a minute, the ball isn't at 2 meters, it's actually at 0 meters according to my ruler. So now we've got a discrepancy between the simplest measurements you can imagine, which is just a measurement of position, right? Two guys in two reference frames would claim that the position of the baseball depends on when you measure the position. Well, you say, okay, but that's not a big deal because I can translate the measurement of the blue guy, the measurement of position in the blue reference frame, I can translate it to the measurement of position in the red reference frame by a very simple formula, right? And I write that formula down here, right? It says that the blue value of x, which tells you what the position of the baseball is just equal to the displacement between the blue and the red reference frames, plus whatever measurement the guy in the red reference frame measures for the position of the baseball. And so this displacement between the two reference frames, x sub f, that's just given by the velocity of the moving reference frame times the time interval t, which is synchronized with this occurrence when the two reference frames happen to be located one on top of the other. So this time interval t is really a time after the two reference frames are synchronized, right? And so with this simple formula, you can always translate the measurement that the guy in the red frame makes to the measurement that the guy in the blue frame makes. And you can put in x prime equals 0, right? Which is what he measures. You can evaluate v sub f times t, where t is 2 seconds. And sure enough, you find that the blue guy is going to make a measurement of 2 meters for the position of the baseball. So knowing one, either x or x prime, you can predict what the other guy is going to measure, and that's great, right? That's really useful because now you at least have a simple formula that connects the two reference frames, one with respect to the other. So this general idea gives rise to this Galilean transformation between inertial reference frames. Here I sketch out the geometry in more detail. I don't specify motion just in one direction. The idea is that we've got a reference frame given by prime coordinates. A guy in that moving reference frame measures the position of an object M, and he makes a measurement and he says that object M is at position R prime, right? A guy in a fixed reference frame would see a displacement between the two reference frames, and that displacement is going to be given by this vector R sub f. And this guy, at the same instant of time, is going to measure the position of the ball, and he's going to get the vector R, right? So again, you got two guys, two inertial reference frames. You get different values for where the position of the ball is. How are they connected one to another? Well, they're connected by this simple formula, which is the general expression for the case that I considered in one dimension. We can also take derivatives, right? So we can ask how the position vector changes with time. That would mean that this guy is measuring this ball to have a velocity u, right? This guy in the moving reference frame would take the derivative of r prime with respect to time, and so he would measure a velocity u prime for that object. And how are u and u prime related? Well, they're related just by the way this vector r sub f changes in time. So this is basically the velocity of the reference frame. And it's also interesting to note that if you calculate accelerations, both guys are going to get the same acceleration, because the reference frame that's moving does not have an acceleration. The velocity is constant, independent with respect to time. So these equations that allow you to go from r prime to r, u prime to u, right? These are known as the Galilean transformations, and they allow you to represent measurements between two inertial reference frames. What we tend to do when we discuss special relativity is we always align the two reference frames. And so that alignment just simply means that the vector r sub f that connects the two reference frames is just given by a component, a displacement x sub f in the I direction, right? There's no displacement in the j direction. And so very often we're always going to discuss this type of a problem where the motion of the two reference frames is aligned, one with respect to another. And we're just going to be asking questions like, if you measure the position of an object in, let's say, the red reference frame, what would be the position of that object x0 in the blue reference frame? And I give the result, right? I give the results here. If you're given the measurements in the unprimed reference frame, you can always calculate the measurements in the primed reference frame using this set of equations. If you're given the measurements in the primed reference frame, you can always calculate the coordinates in the unprimed frame by using these equations. An important feature of this Galilean transformation is the idea that the time interval, t, is equal to the time interval t prime, right? So this is an important equation. Turns out that's going to be an assumption that Einstein questioned, right? And when we do the complete theory of special relativity, this equation is going to be have to be altered. The other point I'll make is there's a very simple formula for velocity addition, right? And that simple formula for velocity addition is going to be the topic of the next lecture, where we're going to test this concept of Galilean transformation for velocities. We're going to apply that to light beams and see what we would predict. So finally, I just wanted to end this lecture by giving you a simple example of a Galilean transform. I think it's simple enough that everyone can understand it. The idea is that we're on the interstate a few miles away from Purdue. There comes a flatbed trailer truck. That flatbed trailer truck is driving at 68 miles per hour down the road. On the back of that flatbed trailer truck, we've got one guy, this guy Cartman. He's got a firecracker, and he stands at 10 meters away from the end of the truck. Right? Now he's going to light that firecracker, and he's going to observe the location when that firecracker explodes, and he's going to compare his location to the location of a stationary observer who's standing on a bridge above the interstate. Right? And so as the truck goes by, the firecracker explodes. We just want to know where Cartman thinks the firecracker explodes and where Kyle thinks the firecracker explodes. And of course, the answer is the two numbers these guys get are going to be related by the Galilean transform. So I work it out in this slide. It's a pretty simple example. All these experiments, or all these thought experiments, require you to line up the two coordinate systems at some time t equal to 0. So what we're going to do is we're going to line up the end of the trailer with the edge of the bridge at t equal to 0. At t equal to 0, the S and the S prime frames coincide. Cartman is standing 10 meters down from the edge of the trailer, right? And he's got this firecracker in his hand. So he lights the firecracker at precisely t equal to 0, and then we wait to see where it explodes. Well, let's say it takes 10 seconds to explode. So in 10 seconds, this trailer moving at 68 miles per hour, which is equivalent to 30 meters per second, right? In 10 seconds, this trailer has moved down the road about 300 meters, right? And when the firecracker explodes, Cartman is going to say, oh, in my reference frame, the firecracker exploded 10 meters from the edge of the trailer. Where Kyle, standing on this stationary bridge, is going to say, no way. When that firecracker exploded, you were 310 meters down the interstate, right? And that 310 meters is just given by adding Cartman's value for the point where it exploded times v sub f t prime, which is the translation of frame S prime with respect to S in the 2 meters, or in the 10 seconds that it's taken for the firecracker to explode. So, one guy gets 10 meters, the other guy gets 310 meters, so they disagree on where the firecracker exploded, but at least they can take their values and translate them back and forth using this Galilean transform, and they realize that there's a consistency between the two independent measurements. So, as a real simple example, it gives the basic idea behind this Galilean transform, and what we're going to do is in the next lecture we're going to apply that to the speed of light and see what interesting contradictions arise. So we'll see you whenever you get a chance to look at that lecture.